we learned a lot of electrostatics. Now we need to go further into the electrostatics with something called scalar potentials. But before learning that, we need to learn about something called vector calculus. That is a backing needed when you learn electrostatics and electrodynamics in general. So we are going into that topic called vector calculus. So as an introduction, let us learn what is a field. That means we are learning about scalar and vector fields. Basically, field means, already we learned field, that is the electric field, and there are many other fields, paddy field or something like that in general. Field means actually it is a distribution of a certain quantity. It can be anything. It can be a wind, it can be a temperature, it can be paddies, it can be rice, or whatever it is. Something is distributed over a space is basically called a field. Now in physics and mathematics in particular, that is, there are two kind of fields that we call it as scalar field and vector field. Now already I told it is a distribution of quantity. In physics there are two kind of quantities, one is the scalar quantity and the other is the vector quantity. So if a scalar quantity is distributed over space, then it is called a scalar field. So let me explain it more. This is a three-dimensional axis, it is a space. Okay, we have an x, y and z axis. Now let us imagine that this is a room, or this is the corner of a room, and we fix three axes to a particular corner, and this space here that represents our entire room. Now at each point there will be a temperature. So we know that in physics temperature is a scalar quantity. So at this point near the floor there will be a particular temperature, and as we go higher and higher the temperature may increase or decrease, and okay, and that means at each point I can associate a value. For example, some 27 degrees Celsius here, and here it is 27.18 degrees Celsius, and at this point some 26 degrees Celsius. So each point in space, not only on this xy plane, in this three-dimensional plane, I can associate a particular scalar, and that particular distribution of a scalar quantity is called a scalar field. There are many examples for that. We can call one of the example is the temperature, a classic example, and there is something called a density. Suppose you have a material. So this is a material, imagine. The material can have different kind of densities. That means it need not be uniform. That is, at the base it has a larger density, and as we go higher and higher there will be the density may vary. Here the density will be higher, and as we go along, for example, the density of air in our atmosphere, it will vary as you go up and up. That means the density of air will reduce as you go farther away from the surface of Earth. So the density in particular is a scalar quantity which has a variation over the coordinates, that means over the space. So to denote that, for temperature we can write it as T, that depends on x, y and z. That means for each value of x, y and z. For example, at this corner of the room the value of x, y and z are 0, 0, 0. That means at this particular point the temperature will have a value. How can we find that particular value? Yes, there is a way that this T will have may have an expression. For example, let me consider some x square y plus z cube plus 3. Let this be the expression for the T. T means that is the temperature field, or it is a scalar field. Now to find its value at the origin, we can put T 0, 0, 0. So for x, y and z put 0. So that means this becomes 0, this becomes 0, and we get 3 degrees Celsius with a particular unit, whatever it is. So at the origin the temperature is 3 degrees Celsius, and at this point there is, imagine there is a point 2, 3 and 6, 2, 3, 6, there is a point 2, 3 and 6. What we have to do, instead of x you put a 3, instead of y you put, instead of x we can put 2, and instead of y we can put 3, instead of 6 z you can put 6. So just calculate its value and you will get a simple number, simple scalar quantity with a unit, and that is called a scalar field. So in reality or in graphical representation, we have another method to represent it that I will discuss later. Anyway, there will be only a number without a direction will be associated at each point, and its expression will be somewhat like this. Some t of x, y, z is equal to a function of x, y and z. There is no vector quantities, no x cap, no y cap or anything. There will be an expression that is about the scalar field. Now, let us discuss about the vector field. So, let us go to so from the previous definition itself, it is clear that the scalar field means, sorry, vector field, scalar field means it is the distribution of a scalar quantity over a space, and here it is the distribution of a vector quantity over the space. That means for each point, now we associate not a scalar, we associate a vector quantity. For example, let me say, let V denotes the vector function, and we call it as a vector function, and we call this t as a scalar function. Well, let V be the vector function, and let its expression be x into x cap plus y into y cap plus z into z cap. So, plus x cap plus y cap plus z cap. Now, we know that x cap, y cap, z cap all represents the direction, and the value of that v, that is the value of that particular vector at a point, is defined by the value of this x, y and z. That means I can define it at any point, I can find the value of that vector. For example, let us find the value of it as, let this point be, before that let me give a coordinate here. So, this is x, this is y and this is z. Now, let us find the value of this v at the point 1, 1, 0. So, I chose 0 because I can draw it in this plane, because z axis is 0 now. Now, that is 1, 1, 0. So, to find that, what I have to do, I have to just input the value, that is instead of x put 1, instead of y put 1 and instead of z put 0. So, what we get, that is equal to 1 x cap plus y cap plus 0 z cap. So, we got a particular vector for a particular point. So, for this, let this point be the 1, 1 point, and I can draw a vector there. So, my vector will be something like this. So, I associated a vector with a particular point. Now, I can draw many vectors. I can draw, and I can take another point. For example, this is 0, 1, 0. So, I can draw one there, I can draw here, and if I finally draw something, I will get something. As you go farther, its length will increase. Okay. So, at each point, this is not only on this plane, I can draw it in the entire space. So, and both in the negative axis, here also we can draw it. Okay. So, I got something that is a vector, a particular vector quantity is distributed over the space. So, when you look geometrically, you can draw an arrow or many number of arrows to represent the vector field, and the expression for that, the functional expression for that will look like V is equal to x cap, y cap and z cap. There will be at least one coordinate or one unit vector to show the direction, x cap, y cap or z. There is no need to have all this together, at least one should be there to denote the vector field. So, that is about scalar field and vector field. You already learned a vector field, that is the electric field. So, we know that is an electric field is, for example, let a charge be here at this point, then the electric field we already drawn it with arrows something like this. Actually, we were mapping a vector field already, or we have already done that in the previous classes while learning electric field lines. So, this is a best example for electric field lines or vector fields, that is electric fields or electric field lines. So, let us go how it looks, how it actually looks like. You can see here, this is actually a scalar field plotting. Okay, now it has an x axis and a y axis on a plane. some arbitrary quantity, and it is actually color graded. That means here you can see the intensity variation, that is when the value of the leftmost color, that is the violet color, is minus 0.32 and its maximum is 0.459. This can be a top view of a hill or something like that. That means at this point it has maximum value, and at this point or this point it has a minimum value, and it is varying. So the quantity is varying. Instead of putting each value at each point, I can put some value here, some plus 0.459, and I can write a value minus 382 here. So instead of writing that, we can use color coding or color grading or false coloring or something like that to show the scalar field. But when you come to vector field, we need something else, that is called these arrows. You can see there is a similar map, that is the wind pattern, and when you look for wind or wind patterns in the global map, you can see some arrows. That arrows exactly shows the velocity of the wind at that particular time. So each velocity is, we know, as we know, it is a vector, and the direction that may be flowing from some coastal side from here to Kerala and something like that, or to India, we can see something like that. So that is what is called a very good example for a vector field. So vector field can be mapped like this. Here you can see each arrow. Here two things you have to get into notice. One is this arrow gives the direction of the vector field, and also its length. Actually its length is increasing. The arrow is not of constant length, that is here it has a length, something a smaller length. When it goes to the red, it length increase. That means the vector's magnitude is increasing. It is also coded in the color form. So in the blue region the vectors are very short, that means the magnitude is smaller, and when you go to the red region its length is increasing or the color is changing to red, that means the intensity or the magnitude of the vector increasing. So this is the way we can represent a scalar field and a vector field in mathematics or in a graphical way. So this is the actual representation that we see in many scientific papers and many things. Okay, now we have already seen something called the del operator. We haven't talked about it much. That is something like this. Okay, when we converted our Gauss's law from integral expression to the differential form, we found a new operator that is called a del, and we call it as a vector operator. Why it is called a vector operator? Because it has a nature of vector, because every time in this expression is associated with a y cap, x cap and z cap. That means it has a nature of vector, but it is not actually a vector because it is a vector operator. It has meaning only when it gets something to acted upon. So it can act with a scalar field, it can act with a vector field in two ways. So it can act with a scalar field as del v. Okay, instead of that let me write. So some del t, let t be a scalar field. So del t, that is some kind of action. Now let us take a vector field. For vector field we always use something like this. We have to use that arrow. This doesn't mean vector v, this means that we can put an x, y, z also here. So that means it is a vector function, not just a single vector. So it can act. So the del can, so del is a vector, v is a vector. So they can act in two ways. That means between two vector you can take two kinds of product already. If suppose you have a vector a and vector b, you can have two kinds of products. That is called, one is called the dot product or the scalar product, and the cross product or the vector product. So scalar product and vector product can exist between two vectors. So one combination of del with the scalar field is this. Now there are two other combination of this del operator with the vector field. They are, one is the del dot v, which we have seen while deriving the differential form of Gauss's law, and there is another form that is del cross v. So they are defined like this. This is the del t, that is the gradient, that is we will discuss what it is later. Anyway, it acts like this. Okay, we will calculate it for some values. Let us wait for that. So, this is called the gradient, that is you have a gradient here, that is you have a to find the gradient, the T, the temperature, we already seen that T is a scalar function, that is for T there will be an expression, suppose x square y. So, instead of this T we can put x square y here, instead of this we can put an x square y here and x square y here. Just take the partial derivatives and you will get an answer with actually T does not have any x cap or y cap because it is a scalar field. But here you can see when you put all these values plugged into this del T expression and find the output, you will get x cap, y cap and z cap there. That means the resultant of that gradient, that is del operated on a scalar function like a gradient, and we got out as an output we got a vector function which has meanings. We will discuss this later. This is one of the form and we call it as a gradient. The gradient acts only between a del operator and a scalar function. There is no del v or del and a vector function, there is no such a gradients. Actually it converts, the gradient converts a scalar function to some other vector functions. Now there is another operation, that is the del dot v. I used E because we already know that E is a vector field. So del dot E, so to find del dot E you have to take the component of E, Ex, Ey and Ez, we will discuss later. Okay. So this is another thing called divergence. Then there is something else called the curl, that is del cross E, which has an expression like this. You have to evaluate this determinant. Now let us go to each of them in particular. So there are three kind of operations mainly. We can find many combination of it, some del square T Laplacian or something like that, but we are not going into that because we need only these three. This is the three basic operation of the del operator with the scalar and vector field, the gradient, the divergence and the curl. So let us go in detail about each of them. Okay, now let us discuss about gradient in detail. So the expression for del T or the gradient is x cap into dot T by dot x plus y cap into dot T by dot y plus z cap into dot T by dot z. Now what does it mean? The answer for that is a vector function, and that del T, so you can evaluate del T for a particular function, we will do that later. So if we evaluate that for a particular function and imagine its answer is something like this, that is some x square x cap plus y x y cap plus z cube z cap, just an arbitrary vector function. This is the answer what we got. What does that mean? What is the physical meaning of gradient? Imagine that this is a scalar function we have plotted in 3 dimension. So this is the maximum value, here there is a valley, and here is some minimum and maximas are there. Now what is the meaning of calculating del T at a particular point? Okay, imagine that, so this is a scalar function plotted. You can imagine it as a height of a mountain, simply it is a mountain, at the mapping of a mountain, and imagine that you are standing at a particular point here. Now we want to know which is the steepest part of the mountain. So you can move along this direction, move along this direction, move along this, but you have a condition that is, or you have a condition in mind that you have to move along the most steepest direction. So if we want to find that steepest direction from a particular point, just calculate the del T of that function at that point. In this case we can call it as some del H, that is the height of the mountain is that function. So if you calculate del T at this point, that del T will points, so del T points means del T is a vector function. So at that point the del T will point towards the most steepest part, so probably this way. Okay, and the magnitude of del T will give you what is the slope along that direction. So always del T will, you can calculate del T, that is the gradient for not only for this height, you can calculate it for temperature. When we are calculating it for temperature, it will show the maximum change of temperature which is the direction in which the maximum temperature occurs. That will be shown by the del T, and what is the rate of change of that? That will be given by the magnitude of it. That is the meaning of the function or the thing called a gradient. Now let us calculate the gradient for a particular function. So, this is a function that is called r is equal to root of x square plus y square plus z square, and this is a scalar function because there is no y cap or z cap. We can plot it using some mathematical tools. So, anyway, this is r, and this is a familiar function. We will discuss that later. After finding the answer for this, you may notice that what is that function is. So, now we are about to calculate the gradient of this particular function. So, for that what we have to do, instead of this t, we can replace it with this function, because we are replacing, because we want to find the gradient of this function. So, for that, then this is equal to, so this is equal to x cap, so x cap into dou by dou x of this r means root of x square plus y square plus z square plus y cap into dou by dou x of root of x square plus y square plus z square dou by dou y. So, plus the next term, that is for z cap into dou by dou z of that function, that same function. I am not going to elaborately doing that because it is very easy integral, it's easy derivative because it is a partial derivative also. So, when we calculate it, you will get something. So, instead of that, we are calculating del r, that means we are calculating it. So, when you do it for the first one, when you do it, you get dou by dou x of root of x square plus y square plus z square, that is 1 by 2 into root of x square plus y square plus z square into 2x. So, and that 2 and 2 get cancelled, and in every time there will be a 1 by root x square plus y square plus z square. Let me take it commonly outside, and the remaining will be x cap plus y cap plus z cap. Now, see that what is this x cap plus y cap plus z cap? Yes, that is our vector r. So, that is vector r divided by what is this root of x square plus y square plus z square? That is the magnitude of vector r. So, vector r divided by magnitude of r means this is r cap. So, r cap is the gradient of this function. What does it mean? So, let us look into a graph. So, actually now I am drawing it in a 2 dimension, but it is actually a 3 dimensional thing. That is, r is a vector function, that is root of x square plus y square plus z square, and it points towards the r direction. That is, this vector is actually, this scalar function is actually the magnitude of our position vector. So, position vector has this direction. That means, if I draw, this is a position vector, this is a position vector, this is a position vector, and all this. So, when I calculate, so, and we do not need the direction because we are only taking its magnitude. Now, what is the most, when we get the maximum change of magnitude, that is the point in question, that is what we got it as r cap. That means, I can stand at a particular point here, okay, then I can move in all direction, towards here, towards here, towards here, towards here. In when you move in which direction, or what is the best direction to move to have a maximum change of this r or this r, that is along r cap. That means, this is the direction of r, you have to move along this direction. Or when you stand here, to have a maximum change, you have to move along the direction of that position vector, that is given by this answer, and that maximum change will be 1, the unit of 1, because its magnitude is 1. That is what is given by gradient. Now, let us go to the next thing, that is called divergence. Okay, now let us talk about divergence. So, as the name suggests, it is a measure of divergence. That means, how much a particular vector diverges out from a point. Here, the expression for this is del dot v. Now, let us see how we got that expression, this particular expression for that. Now, we know the expression for del. So, del is equal to x cap into dou by dou x plus y cap into dou by dou y plus z cap into dou by dou z. Now, v is a vector function. So, in general I can write v as, so there will be a v x component into x cap plus v y into y cap plus v z into z cap. Now we are taking dot product between these two, that this del and this v. Now we know that when you take the dot product, the similar components only products, that means here x cap into x cap is 1 and dou by dou x into v x, that is dou v by dou x. X cap into x cap is 1 and x cap into y cap, that is 0, x cap into z cap is 0. Now take the second one, that is y cap. Y cap into x cap is 0, so there is not such term. Now y cap dot y cap is 1, so dou by dou y of vy, that is the second term, and similarly for dou vz by dou z. So that is how we get that expression. So now we have the expression for that. Now let's see what it means, what it really means, physically what it means. Now here you can see this is actually a vector field mapped, okay, because there are arrows, you can see that it has a direction and a magnitude. Now at this point, you just see that from somewhere over here something is flowing out. So there is a source, or we can call it as there is a faucet is there. Some in terms of fluid dynamics we can say that there is a source is there, there is a fluid source, that fluid is flowing outward. That means if we calculate the value of divergence at this point, we get a positive, because nothing else, the name itself suggests this divergence, that is from here the fluid is diverging out. So when you calculate the value of divergence here, you get del dot v as a positive value, and at this point you can see that it is not diverging, it is actually happening its opposite, that is they are converging. Converging means there is a sink, that is everything come into that. That means it is a divergence, but it is a negative divergence. That is, if you calculate the value of del dot v at this point, then you will get a negative value. That is, if you get a positive value for del dot v, then we call that there is something is diverging out from that point, diverging out. And if it is negative, then we get it as a converging into, okay, that is there is something converging into. So the best example is take a positive charge here. So around the positive charge the field is diverging out. So if we calculate the del dot or the divergence of electric field due to a positive charge, you will get the answer as positive because the field is diverging out. And if we calculate the same for a negative charge, you will get the answer, the divergence as negative. That means all the field points comes into the negative charge. So that is the importance of divergence. That is why that amount of divergence is what we calculated when we learned about the differential form of Gauss's law. So that is what we got it as del dot E is equal to rho by epsilon 0. This is the expression for Gauss's law in differential form. That means it gives the amount of divergence of that electric field. Okay. Now let us go and calculate one particular divergence, that is we are going to calculate that. So before, let me take another example. This is another example. This is not to deal with electric field. Here you can see this is field is spreading out. So there is another simple idea to find if there is a divergence. Just imagine it as a fluid flow, and you are putting some thermocol balls or some sawdust or something of low density. Just sprinkle it over this surface. And if the gap between them, so just imagine that I am just putting some 3 thermocol balls here, 3 or 4, and if the gap between them stays as the same, then there is no divergence. If the gap due to the fluid flow, if the gap between them is increasing, mutually increasing, then we can say there is a divergence, decreasing or increasing. If they come closer, then also there is divergence. Okay. Now see this field, does this have a divergence or a convergence? At first look we may think that there is no divergence or convergence. So let us use that simple trick of balls, that thermocol balls. Let me put one ball here, one ball here, and one ball here, one ball here. Imagine that it is a fluid flow and this arrows represents its velocity. Now we know that the velocity at this point is faster than that here. That is why? Because the length of the vector is larger or longer at here and shorter at here. That means these two balls will move faster than this. That means after some time, if you look, these two balls will be here, these two will be here. Since the gap between them increased, there is a positive divergence. So this is about divergence, and let's calculate the divergence for a simple vector, that is v is equal to x cap plus y cap plus z cap, and we know that to calculate that, what we have to do, this is the x component of the vector, put it here instead of vx, that is the x will go here, this is the vx in this vector, vx is x and vy is y and vz is z. So put each of them there and we get del dot v is equal to dou by dou x of x plus dou by dou y of y plus dou by dou z of z. Each of them will value 1. So the total is 3. That means it's a positive value and we got a positive divergence. So let us plot that. How do this field look like? This field is simply the radial vectors. So if you plot each of them, you will get something like this, which is what we seen in the previous picture. So this will be already by plotting itself, we can see it's a diverging field, and we got it by simply without drawing it, we calculated it using the mathematical technique called divergence. So this is the physical meaning, how much a vector spreads out from a particular point is given by divergence. Now the next thing we want to learn is curl. We will discuss about that in the next session.